Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my second video on Chapter 2 of my series on the Math Lovers book. For those of you just joining me in this series, it's a it's a series on a three-volume series of books I wrote from 2019 to 2022. Each of these books is available on Amazon.com in case you're interested in buying them. You can either search for the Math Lovers book or for my name, David Tare, and you'll find it either available in paperback for $30 a piece or Kindle for $9 a piece. And I do recommend them if you're interested in math like I am. Just to give a little overview, the volume one, which is the one I'm going through now, has 10 chapters on kind of recreational areas of math. And it's kind of high school, advanced high school level, but it's fun, I think, especially if you like math. And volume two is a little more academic. It's on kind of undergraduate level, maybe first year or second year undergraduate level math. There's a few sections on calculus. There's also some stuff on functions and on probability and statistics. And then the third volume is a problems and solutions manual for the first two volumes. It has a set of problems pertaining to the first two volumes, and then solutions, all the odd number problems. The even numbers you have to solve yourself, because in real life there's no solutions that are given. So anyway, that's just an overview of the Math Lovers book. But anyway, let's begin with today's lesson. So, like I said, this is my second lesson in chapter 2, and today I'm starting on primes. And the first thing I'm going to talk about is factoring. So, anyway, let's begin. So let's first start by defining prime numbers or primes. And before I do that, I just want to say a little bit about prime numbers. I think most of you guys will know what they are. I have the definition on the bottom here. Prime number is just a positive integer greater than 1, such that the only two factors are 1 and the number itself. And 1 is not regarded as a prime number, even though it has only one factor. It's called a unit. One's kind of a special number, but every number greater than 1 is either prime or composite. And prime just means it has only two factors. Composite means it has more than two factors, and it turns out for every composite number, you can always find two numbers greater than 1, such as the products of those two numbers. That's what composite means. And when you write a number as a product of two things greater than 1, that's called a factorization. So today I'm going to talk about factorization or factoring. And I think I already said what it is. And factoring is very important. I mean, there's a lot of applications of factoring. I think the most important application, which I don't talk about in this book, but there's something called the RSA crypto system. And that's how that's the standard crypto system that's used for securing all your bank information, all your passwords, all your personal information that's kept private on the web. All your accounts on everything you use on the internet. And it relies on the difficulty of factoring very, very large numbers. I'm talking about numbers with like 600 digits that are product of two primes and with about 300 digits each. Nobody knows how to factor those numbers quickly, and that's why they're secure. But if anybody did figure out how to do it, then we'd have to get a new security system in place, a new crypto system. So let's hope it remains secure for the time being. Anyway, so that's just one application of factoring, probably the most important one. But how do we factor numbers? I'm not talking about huge numbers because those are really hard to factor. But there is a trick, and you probably learned this in grade school. There's something called factor trees. This is the most common way that kids learn how to factor numbers, and we can factor pretty large numbers this way. I'd say, I've never seen any homework problems involving doing factor trees of numbers bigger than 1,000. So smallish numbers, numbers with up to 3 digits, you can do fairly easily using factor trees. And I'll just give you some examples. Maybe this is a little bit of a review of some stuff you learned in grade school, but this is a very useful thing to know, so it's probably good to go over it with an example. Let's try to factor the number 60. And I'm going to do this with two different factor trees. So what a factor tree is, you start with a number, in this case 60, and 60 happens to be composite. I mean, it's pretty easy to see it's composite because it's got a lot of factors, and besides it ends in 0, and there's no primes that end in 0. As a matter of fact, 2 is the only even prime. Every other prime is odd. So since 60 is even and it's bigger than 2, we already know that it's composite. So the first thing we have to do is we have to find two non-trivial factors of 60. Well, that's pretty easy. 60 is divisible by 10 since it ends in 0. So 10 is obviously a factor. And if you divide 60 by 10, you get 6. So here's how we can start the factor tree of 60. We make two branches going down. So 6 on the left since it's smaller, and 10 on the right. Those are two non-trivial factors of 60. That's how we start the factor tree. And those are the first two branches. This is up to level 1 of the tree, if you like. And then we just do the same thing on these leaves. The number of nodes, if you like. The number is on the end. Level 1. So 6. I think it's pretty easy to factor 6. That's also composite. 6 happens to be 2 times 3. So we put two leaves below 6, 2 and 3. And then we do the same thing for 10. 10 also has a non-trivial factorization, namely 2 times 5. So we draw the leaves 2 and 5 below 10. And now it turns out the numbers on the bottom are all prime. It's pretty easy to see that. 2 is prime. 2 is the smallest prime, and it's pretty easy to see that the only factors of 2 are 1 and 2. And similarly for 3, 3 is also prime. The only factors of 3 are 1 and 3. And also 5. 5 is also prime. Only factors of 5 and 1 and 5. So we're done. Every number on the bottom, these are called the leaves of this factor tree. Every number on the bottom of this tree is prime. That means we can't go any further. So now what we've done is we found what's called the prime factorization of 60, or at least a prime factorization of 60. It turns out that prime factorizations are always unique. That's a fundamental theorem of arithmetic. That's a very difficult theorem to prove, by the way. I do prove it in one of my videos I made about a month or two ago on number theory, but the proof is very advanced. To prove the fundamental theorem of arithmetic, you have to know some pretty advanced number theory, which most people never learn. But just take my word for it. It's true. It's a very important theorem. I don't know who the first person to prove. I think it was Euler who first proved the fundamental theorem of arithmetic. He was a math genius by any measure. A lot of people consider him the greatest mathematician that ever lived. But I believe he proved the fundamental theorem of arithmetic, and the proof had to wait until the 18th century. So, the Greeks who came up with prime numbers, they were never able to prove it. It was never proved during the Middle Ages. It wasn't even proven during the early Renaissance, even though everybody knew about prime numbers and factorization, well into Renaissance and up to the 18th century. Nobody knew how to prove the fundamental theorem of arithmetic until Euler in the 18th century. But anyway, so now we have what's called we have the prime factorization. Then you just read the leaves on the bottom of this factor tree. We have two factors of 2. We kind of gather them from smallest to largest. So there's two factors of 2. So we can write 2 times 2 for those factors. And then we've got a prime factor of 3. So we write 2 times 2 times 3, and we're left with 5. So we just say it's 2 times 2 times 3 times 5. Or if you like, 2 squared times 3 times 5. That is a prime factorization of 60. And just to convince yourself that this is unique, we can make another factor tree. Factor trees are not unique, but the leaves on the bottom always turn out to be unique up to ordering. So let's factor 60 another way. And there is another way to do it, 5 times 12. There's actually a lot of ways you can factor 60. I just picked a second one. So 5 times 12 is another non-trivial factorization of 60. And now we do the same thing we did before, except the node on the left, the 5, is prime now. So we can't do anything more with that. So we leave the 5 alone. That's a leaf. But we can still work on 12. 12 has a non-trivial factorization, namely 3 times 4. Now we do one more step. 3 is prime, so we leave that one alone. But 4 is 2 times 2, or 2 squared, if you like. So again, if you read the leaves, now we're done, because 2 is prime too. So now if you read the leaves, going from smallest to largest again, you still get the same thing as we did before. 2 times 2 times 3 times 5, or 2 squared times 3 times 5. So even though we got a different factor tree, we got the same prime factorization. And this is always the case, it turns out. This is what the fundamental theorem of arithmetic says. It says that no matter what factor tree you come up with for the number you're trying to factor, any number, doesn't matter what it is, any positive integer, you're always going to get the same prime factorization when you're done. And that is what's known as the fundamental theorem of arithmetic, and here it is spelled out. So every natural number has a unique prime factorization up to ordering of the factors, of the prime factors. And like I said, that wasn't proven until the 18th century by Euler. So anyway, that completes my video for today on factoring, my first video on prime numbers. And prime numbers have a lot of other important applications, which I'm going to get to later on the next few videos. So anyway, just stay tuned for that. And thank you for watching, and long live math, and I'll see you guys next time. Bye.